All right. So I think we're starting. So hello. What we're going to do today is we're going to take a break from discussing computation complexity. So computation complexity is something that's going to stay with us for at least the next 3 months. So it's going to stay in 2190. So don't worry about it. I want to do an application of dictionaries, which actually is going to play later on also into analyzing computation complexity. And then we'll just introduce project 3. So the first thing that I want to introduce is this idea of using dictionaries to store sparse matrices and vectors. So the idea is like that. So first of all, what's a sparse matrix or a vector? It's kind of a vague concept. So matrix where most of the entries are 0. All right. So the idea is kind of like this. So first of all, how do you store a matrix? Well, you might store it like this, right? So it would be a list of lists, something like this, for example. And then, of course, it's not MATLAB, it's Python. Python doesn't know that it's a matrix as far as it's concerned. It's a list of lists. It just so happens that the length of the first row is the same as the length of the second row. So that's what makes it a matrix, right? Is that all the lists are of the same length. And then so we saw one example of that. So if you want to access, for example, this 6 over here, what you would say is m at 1. So m at 1 would get you this guy. And then m at 1 at 2, that would be the 6. Right? So that's something that we saw already. So what happens if m is really sparse but really large? So you might imagine that it would look kind of like this. So there's going to be like lots of zeros and lots of zeros over here. And maybe there is like one thing that's not 0. So you might imagine that if this is extremely large, it would be very inefficient to store all those zeros if really all the information that you need is that there is just the 1, 5 at location 1, 2. So instead of doing this, instead of storing n times m entries, so for whatever n rows, m columns, most of which are 0, just store the information about where the non-zero entries are. And then the rest is just zeros, because you know which are the non-zeros. So how might you do it? Well, you might use a dictionary. So we'll say we have this sparse matrix, and it's going to be a dictionary. And in this case, let's say that it's all zeros and just 1, 5 at location 1, 2. So that's what we'll store. So we'll say this key, so this is a tuple, 1, 2, that corresponds to a 5, everything else is 0. Done, right? So we've stored potentially a huge matrix by just doing this. Now, one more piece of information that we need, what is it in order to be able to know what matrix it is? Like if we just have this information, that's not enough, right? Yeah, exactly. We need the size, right? Because if you add another column that's zeros, that's not reflected here at all, right? So you might just say, well, like the size is whatever. So definitely 2, it needs to be at least 2. And then here it needs to be at least 3, but it could be extremely large, right? So that would take a lot of entries in order to store using a list of lists. But here we just said, okay, we have this one entry, and then we know that the size is this much. So we can print this matrix. So it'll take the actual matrix and it will take the size. So what do we need to do here? So we need to print basically a bunch of zeros except for the entries that are non-zero, right? So we got to print everything, so we might as well do a loop, right? So I'll say, okay, so for row in range, so this would be size 0, right? So this many rows. And then I'll say for column in range size 1, so this many columns. So for now, I'll just say print 0, and then here I'll say end is nothing. In fact, I'll do a space, right? So that's not going to be super pretty. We'll fix it up, but that for now will print just all zeros, right? So I try this. So I'll say m sparse, and I'll give the size as whatever 2 by 7 for now. So I run this, and that of course is a problem. So I'll comment this out. And here we are. So I didn't add a line break. So here I'll add just so I'll just say print nothing. And what that'll do is once I'm done printing all the entries in row 0, I do a new line. And then after I'm done printing all the entries in row 1, I do a new line and so on. So I run this. That's going to be a nice 2 by 7 matrix. That's all zeros. So what I want to do now is instead of the zeros, where appropriate, I actually want to print the entry. So how can I do it? So the easiest way to do it is to just check, does it happen that the entry should be non-zero? So I'll just check. So if row column is in m sparse, and remember what this notation means is I'm checking whether this tuple is an element, is a key in m sparse. Then I'll print m sparse at row column. And otherwise, I'll print my 0. Make sense? So by default, I print 0, but I check every time. Is the tuple, hey, is the tuple row column in m sparse? So that's like this, and I forgot and is equal to space. So that makes it so that when I print, I don't print a new line automatically. And that gives me my nice matrix. So this prints nicely. By the way, this doesn't really matter much, but this only prints nicely if I have entries that are single digit. If the entries are not single digit, it'll be kind of ugly. So like this. So what I can do is, instead of saying that the end is this, I can make the end be tab. And this works when you're writing text as well, right? So tab specifically makes it so that everything is displayed nicely when it's a table. So that would be kind of like this. I need, of course, to say tab here as well. And that would be like this. And then if I make it 51, that's still fine. So that still prints nicely. Okay, so that's just like if you press the tab button when and you probably don't do that often, but if you're just writing text and you use the tab button in text, that'll do the same thing as well. It'll align the columns. All right. So, okay, so this is how you can print a sparse matrix. So that's cool. So let's do something slightly more. So by the way, of course, you can have more than one element. So we can put something at 0, 0. So let's say 0, 0 is 42. That is now going to be like this. So that's nice. So let's do just one more example. So let's say that I want to add two sparse matrices. So M1 and M2. So what's the idea here? The idea here is, let's say you have this guy and you also have this guy. So let's say that this is 10, and then this is 12. So what's going on here? So we have one matching entry. So we have 1, 2, and 1, 2 here matches. So this means that at this location, one matrix is 51 and another is 10. So the sum should be 61. Here we have 0, 0, which doesn't match. So at this location, it should be 42. And then at location 0, 1, so this guy, the sum should be 12, because 12 plus 0. Make sense? Questions? So, okay. So what can we do? So we basically need to construct this new matrix that's the sum of the two. And we need to go through every location that's not 0. Everything else is going to be 0 anyway. Right? So one thing we can do is we can say, okay, all right, so for chords in M1, so I'm going through every coordinate M1, so it's going to be 1, 2, and then it's going to be 0, 0. This is going to be sum at chords. What is it? It's the sum of M1 at chords plus M2 at chords. So remember, what for chords and M1 means is that chords is first 1, 2, and then it's going to be 0, 0. So that's not enough. Why is this not enough? Anyone? Yeah. Yeah. So if chords is in M2, then we haven't considered it yet. But that's okay. I can just say for chords and M2, and I'll just do the same thing. So is it the problem that I'm going through pairs of chords twice? Well, not a big problem, because it's not as if I'm adding again. I'm just recomputing some stuff. Right? Yeah.
And then also, if the coordinate in matrix 1 isn't is 0.
Yeah. So that's another problem. So here we're saying, okay, so coords is definitely in M1, it might not be in M2. So you could do it with an if statement, because like if you try it, right? So if you say M sparse 1 0 0, well, define M sparse 1 first. That would be a problem. That would be a problem if I say M sparse 1 at 0 0. Well, that is actually fine, 0 1. That would be an error. So one thing you can do is you can use the get function. So if so this is kind of like the square brackets, except by default, if you ask for something that doesn't exist, it'll just return none by default. And you can specify what you want by default. So something like this. So this would be M sparse 1 at 2 2 by if available, otherwise 0. So here we can say get coords, and if M2 at coords doesn't exist, just plug in a 0. Similarly here, we'll say M1.get, and then coords, and that's a 0. And that's like this. And then we're done, and we can return the sum. Make sense? Questions? All right. And that potentially, so in some applications, you have kind of, a lot that you can do if you do. So if you need to store something that looks like a very big matrix, except most of it is 0, it happens in all sorts of applications. So like in remote sensing and stuff, and also in project 3 as it happens. So we'll talk about project 3 in a second. I'll go on Discord, and you should go on Quarkus and do the quiz. It's not difficult today. Is the quiz is hopefully there, is it? No? Yes? Okay. All right. What? Seriously? But I put it there. Wait, they removed the question again? Oh man. We're like running out of lectures to have the 12 quizzes. Okay, quiz 6 is canceled. There's gonna be a quiz 7. And that one is gonna be good, I think. Okay, so I'm literally putting the question here in front of your eyes. So. Okay. Yes, it's definitely there. Go do it. So, okay. All right. Yeah, so do it before Quarkus steals my question again. Okay. So I want to talk about word embeddings. And that's kind of what project 3 is all about. Specifically, this is kind of what project 3 looks like. So you want to figure out, without using a dictionary, which words are close together in terms of meaning. So close together semantically, people say, and which are far apart. In order to operationalize this, it's kind of like what you would see on kind of the SAT or the TOEFL or something like that. So which word is closest to nifty? Well, like probably groovy, right? Is the right thing. Okay, depending on your age. So we want to do it without a dictionary by just ingesting a bunch of text. So the way that kind of ChatGPT does. So here's the basic idea. So how related are two words? So linguistics has this thing called the distributional hypothesis. And the distributional hypothesis says that words are related if they appear together in similar contexts. So the idea is that, for example, words like dog and canine would appear in similar contexts. So like food and veterinarian and park, whatever. And then words that are like different, like dog and astronaut, are going to be not really appearing together in many contexts. So what we're going to do is we're going to compute for each word which words it occurs with in a large corpus of text. So corpus just means like a collection. Right, so specifically, we're again going to go to Project Gutenberg, and we're going to download some public domain novels. We're not OpenAI, so we can't do like non-public domain stuff, which they definitely do. Yeah, so we're not going to do it. Okay, so the way we're going to do it is we're going to say, okay, like for each word, for example, dog. How many times does it appear together with homework? How many times does it appear together with that veterinarian? How many times does it appear together with school, and so on? And the idea is like it's good. It's a good exercise for kind of using dictionaries. It's also a little bit kind of what GPT does as well. GPT is kind of more sophisticated. So what is Discord saying? The quiz still isn't there. What is like the quiz isn't there?
It is. It's in grades. It's normally in the science class, but it's in grades. So there's something grades.
All right. Can someone go on Discord and tell the people who are lost how to find the quiz? I have no idea. Don't use Quarkus. Okay. Please, someone who found the quiz, please go on Discord and tell them where to find it. So okay. So this is what we're gonna do. We're going to say each word is kind of this vector. And the vector represents how many times which word appears together with which other word, right? So here it would be that student occurs with university 50 times and with homework however many times this much. This is. And then scholar occurs with university 70 times and a little bit less with homework. And then dog just occurs with homework and eat. It does not occur together with university, so that's why dog is over here. Make sense? And then you're going to say, well, like if we can represent those words as vectors, we can just say that vectors that are close together are going to be similar in meaning, because like what does it mean for them to be close together? It means that they kind of occur together with different words in the same amounts roughly. And then vectors, words that have vectors representing them that are far apart, well, those are going to be different in meaning. So going back to this kind of task, we're going to say what vector is nifty, what vector is thrifty, and so on. And the hope is that nifty and groovy are going to appear together more often. So the vectors that represent them are going to be close together. Make sense? And like, why would it be? It would be like nifty. That's a nifty project. That's a groovy project. So they occur together with project, but shifty does not appear together with project. I'm going to get caffeinated and do the project. That's going to happen. So caffeinated is going to appear together with project a lot, but possibly with other words as well that don't occur with project, whatever. Make sense? So, okay. So how do we operationalize that? So two things. So one thing we need to figure out is how to store those vectors. And another thing we need to figure out is, like, once we store them, how do we actually say those vectors are close together, those vectors are far apart? There's several ways. So let's say that they have two vectors. So V1 is this. And V2 is this. So first of all, how is it going to look like? So it's going to be that, like, one word, how many times does it appear together with dog? And how many times does it appear together with cat? And how many times it appears to get together with quiz, and so on. And the entry here would be this word with dog. The entry here is this word with dog, and so on. Right? So, okay. So how close and how far? So this is, by the way, not lists. This is just vectors represented with square brackets. In fact, we're not going to store them using lists. So how do you figure out whether two vectors are close together? So one thing you can do is just say, how far apart are the endpoints of the vector? Right? So, like, what's the distance between this point and this point? This is kind of like, what's the difference between student and scholar in terms of, like, in this 3D space. So if that's what you're doing, you could say the distance between V1 and V2, and this is going to be like the Euclidean distance, is what it's called. So that's going to be like the square root of whatever, V1 at 0 minus V2 at 0, and this is squared, plus the same thing for 1. And so on. And that's one way to do it. And in fact, it works okay. Now, one argument that you can make is that's not exactly what we want. And the reason might be kind of like this. So let's say that we have dog and we have canine. So the thing about canine is it appears much less frequently than dog, but possibly in the same contexts. So what you might imagine is that the vector for canine is going to be in the same direction because it occurs with homework and with eat in the same proportions as dog. So let's say it occurs with eat 5 times as often as it occurs with homework, because dogs eat like 20% homework and 80% other stuff, right? But it's going to be shorter. So it's going to be a vector that's kind of like this. If that's the situation, so if canine is over here, then the distance between the endpoints of canine and dog can be quite large. However, by the argument that they just made, the angle between the vectors is going to be not very large. Make sense? So how do you compute the angle between two vectors? Well, there's actually a formula. So if we're talking just two-dimensional vectors, then and in fact, even if it's not two-dimensional, the cosine, that's just, I'm not going to prove it, but it's true. It's going to be V1 dot V2 divided by the square root of norm V1, norm V2. All right. So that just in fact, sir. So the square root is if it's squared. So that's just this is called the cosine law. And that's true in 2 dimensions, but it's also true in any dimension. So the cosine of the angle between V1 and V2 is like this, where this is the dot product. And this is the product of the norms. So the norm is this. Okay. So what we can say is, well, the vectors are very similar if the angle between them is small, meaning that the cosine is as close as possible to 1, because cosine of 0 is 1. Make sense? So pulling back, what we're going to do is for each pair of words, we have this pair of vectors where how many times does V1 occur with dog in the sentence, with cat, and so on, with quiz. The same for V2. And then we can say, well, like if the Euclidean distance between the endpoints of the vectors is small, then they're similar. Separately, also, if the angle between the vectors is small, then they're similar. And angle is small means the cosine of the angle is large. And large means larger than 1. It can't be larger than that. Make sense? So when we're writing the assignment, what we do is we say, okay, like we have a vector for nifty, which is the vector that's closest. So by default, you're going to do the cosine of the angle. So for which vector has the smallest angle with the vector for nifty. And that's going to give you kind of actually a good idea of which words are close together. And again, kind of the neat thing here is that you're doing it without looking it up in the dictionary. You're just looking at how the words are used. And you'll see that it actually works. So that's pretty cool. So this is kind of like one thing that you can see. And we are doing something that's like not super sophisticated and that doesn't take a lot of computing power. It can run if you do it efficiently in like 10 seconds. Also, kind of to train something like GPT, that's like many orders of magnitude more. So this is kind of intermediate. You would not see this kind of effect if you try it with the vectors that you compute. But this is called embedding. So embedding in the sense that you're putting the discrete words into n-dimensional space. That's what embedding means. And word2vec is something that's at this point old hat. This was like, I don't know, 10 years ago. What people found is that if you do embeddings using word2vec, which is a different algorithm for what we are doing, but kind of same principle, it turns out that you can do this kind of weird math with the word vectors that you obtain. And what you can see, for example, is that to move from the vector for king to the vector for queen takes you the same, you need this to go in the same direction as going from man to woman. So you can kind of take the vector for queen and then add the difference between the vectors for man and woman, and that will get you approximately to the vector for king. And similarly, you can like conjugate verbs and stuff. So you can get to swimming, from swimming, I guess, to swam by starting at swimming and adding the difference between walked and walking, and you'll approximately get to swam. Similarly, you can do it with like capitals of countries. So that takes, so what you're doing is you're doing 2 novels. I think I asked for like one by Marcel Proust and then War and Peace or something. And those are like famously long, but still kind of a couple of megabytes each. So this was trained on kind of a couple of gigabytes. That's what it takes to get this kind of thing. And then kind of ChatGPT trained on an undisclosed amount, but presumably kind of getting to like the thousands of gigabytes at least. So that's kind of the difference. All right, so the thing that's left is how do you implement this? So one problem that arises is that you have a lot of distinct words, right? So in general, English has like a couple 100,000 words in English in general, but that's not counting proper names, so like names of people, like names in like French or Russian novels, of course, are not like part of the English language. So you'd get kind of like a couple just like as an estimate, like probably this many words. And then if you wanted to store without using sparse matrices, all the concurrence numbers, that would take 200,000 squared entries, which is like not a little bit. So instead, what we're going to do is we're going to say, well, like actually, like most of the 200,000 words don't concur with each other at all. So we're going to use sparse vectors in order to store this kind of deal. So what we're going to do is we're going to say we have our embeddings. And we're going to say the embedding for dog is initially going to be this kind of dictionary as well. And then we're going to say dog occurs with homework, whatever, 200 times, and then dog occurs with park. That's probably not the case in War and Peace, 500 times, and so on. Right? So what's the idea here? It's not that Python knows that you mean that it's kind of like a matrix, although it kind of looks like you're putting something in a matrix, right? You're saying like at coordinate dog, at coordinate homework, put in 200. What's going on is that this is a dictionary in the same way that when we have a list of lists, like M at 0 is going to be a row. So this is a dictionary. And then we're saying for the dictionary that corresponds to dog, for homework, enter 200. All right. So that's your job for project 3, is to basically set it up. So one thing I want to say actually has to do with computational complexity. So one way that people often try to go about it is they're going to say, kind of like what I just entered here. Like I need to compute M at dog at homework and also M at dog at park. And what I'm going to do is I'm going to go through all the possible words. And then for each word, I'm going to go through all the possible words and figure out how many times they occur. That, again, gets you into the 200,000 squared territory of how many times you need to do the update. And that takes a few days if you run it on your computer, probably. Okay. And formally, the reason we say it is so this is what not to do. So I'm writing it because that's like the wrong thing. And the reason it's a bad idea is because this is O of n squared, where n is length of all words. Of course, right? You're repeating the same thing. Like for each word, for each other word, compute the co-occurrence. So that's O of n squared. And actually, like that's where complexity analysis helps you in practice, not the thing that you want to do. What you want to do is go through each sentence. And for that sentence, say, inside the sentence, what are the co-occurrences? Update all the co-occurrences as you see them in this sentence. And then move on to the next sentence, move on to the next sentence, and so on. That way you avoid the O of n squared behavior, because inside the sentence, there is k-squared pairs where k is the length of the sentence. And sentences are quite short. So technically you could say, well, that's also O of n squared. If the entire novel was one sentence, that would still be actually the same algorithm. But actually, because sentences are limited in size, that's actually just linear in the number of sentences. So I'm not going to do the full analysis. As you write it out, you'll see that it's linear in the number of sentences, and the complexity, if you do it that way, doesn't have to do with the number of words that you have. Or does, like insofar as the number of words is proportional to the number of sentences. All right. So that's that. All right. Questions about any of this? Yes.
Go to the top. You are comparing some word V1 to a list of three-word dot categories. What determines which words we should use as the axis for the vector?
It's all of them.
All of them?
Yes.
Oh.
So all the words in the corpus.
Okay.
Yeah.
So is the similarities between dog and homework stored in one place, and the similarities between homework and dog?
So you don't store the similarities because that's again 200,000 squared. So you compute them as needed. Right. So here, when you're asking, which is the closest is meaning, you compute 4 similarities kind of on the fly. All right, well, we did the quiz, we introduced the homework. Let's go. I'll see you Wednesday. Bye.